In this video, we're going to talk about specific gravity. I know what you're thinking. Specific gravity? Why do I need to know about specific gravity? Specific gravity was one of those weird little things that was introduced in a general chemistry class, maybe in middle school or high school, or even in our college chemistry, Chem 151 and 152. They just spent 2 or 3 minutes on it and then they moved on because they told me the most important thing here was something called density. And I didn't really need specific gravity. And they told me at the time that I could take my density value and I divide by 1. And by dividing by 1, this gives me specific gravity. No, that is far from the truth. Far from the truth. So we need to give specific gravity its due justice. And when I say that, what I'm talking about is that in real life, not in a classroom, in real life, ta-da, specific gravity is where it's at. Everything that we do is specific gravity based. If this is a real working laboratory, chances are most of the time I'm going to be reporting specific gravity numbers. I'm not going to be reporting density values. Density, yes, absolutely, it gives us an idea of how to get there. But it is far from the truth if you have been told that density is more important than specific gravity. Also, if you have been told that take your density and divide it by 1 and you get specific gravity, they're the same value. No, that's wrong too. That's nothing. Oh my God, I can't even know. I don't even know where to start. We don't divide by 1. The reason they told you to divide by 1 is because they told you at the time, probably, that the density of water is 1 gram per milliliter. No, that's wrong too. It's not 1 gram per milliliter. Sorry. So I feel like it's been a sham, don't you? All of that knowledge that you absorbed like a little bitty sponge, talking about density and how to calculate density. And once you get density, divide by 1 because that's specific gravity. And we divide by 1 because the density of water is 1 gram per milliliter. That's all that we've got to do, right? No, that's actually not. So we need to take a few moments. A few moments probably means hours worth of lecture. And we need to talk about specific gravity, General Chapter 841. So this is coming again from the USPNF. But the USPNF, the reason that we focus on this, yes, we're doing monographs. Yes, we're doing pharmaceutical type of work. However, this particular definition and the way that we calculate it in the USPNF is really how all of life calculates specific gravity, except for academics. Go figure. So General Chapter 841 is going to be found in the wonderful, great USPNF, United States Pharmacopoeia National Formulary. Woohoo! Look at me, I sound smart. And here's General Chapter 841. So there's a chance that you have a copy of this. There's a chance that I passed it out. There's a chance that you can look at this and scribble little notes all over it as we begin to talk about what specific gravity is and how is it different than density. So this is the document that we're going to be referring to, and we'll keep coming back to this, and we'll keep dissecting it little bits at a time to see any kind of weird thing that I need to pay attention to when we measure specific gravity and report specific gravity in a laboratory environment. All right, so first off, I think that the best practice here is to, yes, go back and talk about density. So in order to get a good grasp of what specific gravity is, we do have to understand what density is because it really corresponds to what we're getting ready to do. So back in the day, if you've had another science course, maybe you have, maybe you've not, but you could have seen this already, and they have told you that density can be calculated as long as you know the mass of the material divided by the volume or the amount of space that it takes up. And a lot of people will say, Well, density is really to related how heavy the compound is. Well, kinda. I mean, it's a very loose definition, and if it helps you to understand density that way, you're more than welcome to kind of relate those two things together, even though that's not really a true definition. So, in order to calculate density of any type of material, it means that I need the mass of that material that I'm working with, and I need the volume, which is the amount of space that that material takes up. Now, when I say material, what I'm talking about here is actually matter. There are three major states of matter. There's more than three, but three major ones. And the first one is something that we call a solid, and then we have a liquid, and then we have a gas. All three states of matter. Pretty typical. They didn't lie to you about that. Good job. And the reason that I'm bringing this up is because depending on what state of matter that we have, very often the units begin to change on us. So if I take a liquid, I can easily obtain the mass of a liquid. I just go to a balance and I pour that liquid onto a balance, and I can record the grams that that liquid will mass. I can also calculate, not even really calculate, measure the volume of a liquid very easily. And that volume can be measured in terms of milliliters. So I can pour liquid into a graduated cylinder. I can read the volume of that liquid. Let's say it's 50 milliliters. Great, that's the volume. I mass that 50 milliliters that I just poured out in that graduated cylinder. Great, there's a gram. And then I take that gram and I divide it by the number of milliliters, and that gives me a density read, the density of that liquid. If you've had 114 with us, we've done a density lab, and that's exactly what we did. We had a liquid, we poured it out, measured it, took a mass, volume, divided it. Great, good job. Solids, though, are also another state of matter, and solids have a density value that comes along with them as well. And that density is still in terms of gram. There's no difference there. But I can't necessarily pour a solid into a graduated cylinder to get a volume. It's a little odd, right? I could have a regular shaped object, and that is maybe something like a cube, or I could have an irregular shaped object that's just like a chunk of material that's been broken off of a big slab. So how do we go about calculating the volume? Well, I'll talk about that in a minute, but the unit here, because of that, is different. It is not in milliliter. Instead, it is in terms of cubic centimeter. Centimeter times centimeter times centimeter. Oh, well, if you ever did some measurements, if you ever did some construction, if you ever calculated the areas of something, I think that 3 dimensions are going to be pretty common for you, because this is like the length times the width times the height, right? And I can measure the length of that object in centimeters. I can measure the width of the object in centimeters, and I can measure the height of the object in centimeters. Yay! And I take centimeter times centimeter times centimeter, and that is cubic centimeters. So that is one of the reasons that the unit changes. It's just more formal to report it that way. But here's the magic, ladies and gentlemen. Cubic centimeter is actually equal to a milliliter, if I'm talking about water most of the time. And a cubic centimeter is also known as a CC in the medical world. Hurry, give that person 5 cc's of some kind of sedative to knock them out because they've watched too many Chemtech videos. Well, 5 cc's means 5 cubic centimeters. 5 cubic centimeters probably means really darn close to 5 milliliters. It's just a matter of the point of reference. So the unit for density of a solid is gram per cubic centimeter. The unit for density of a liquid is gram per mil. And you need to understand that these two are very often the same value, because a cubic centimeter is often related to a milliliter, 1-to-1 ratio for the most part. Now that leaves us with gases. Gases, well, it's kind of odd. We still measure them in grams. That's not a big deal. But in order to get grams, we need quite a big amount of gas in order to get a gram amount. So this takes a larger space. This requires more of it. And because of that, more room is needed. So no longer are we in cubic centimeters and milliliters anymore, but now we regard density terms of a gas in terms of liter. So, density of a solid, gram per cubic centimeter. Density of a liquid, gram per mil. And density of a gas is gram per liter. That is what we're after. That's what we calculate. That's what we do the most. All right. So, in order to calculate density, looks like I just need some masses on a balance in some form or fashion. It looks like I need a way to measure the volume in some form or fashion. And as long as I have those two pieces of information, I will be able to calculate this value. The shorthanded equation for this, if you've not had it before, is D equals M over V. Density equals mass divided by volume. All right, so that's a little bit of intro on density, but at no point in time have we talked about specific gravity yet. Notice I've not lied to you. I've not said divide by 1. I've not done that, and I'm not going to, because that's not proper. So very often, we like to show images. Ooh, it makes them all nice and pretty. And the images will help hit home a message, I think. And this image, even though it's not necessarily scientifically correct for the most part, but it at least drops home a message, and that's what we're all about, is comparing the density values of solids and liquids and gases. So what you're seeing here to the left, here is a gas bubble, and those gas particles hate each other. They cannot stand each other, right? And there's a lot of empty space in between them, a lot of room between one neighbor to the next. And it makes them very happy because they don't get along. They don't want to be near each other. They want to fill up as much space in Brunswick County that they can, because the more space that they take up, the less things and people that can move here. And that makes us all happy. Well, that's a gas. It's a representation of a gas. But notice all of this empty space that's here in between these individual particles. That empty space, think of it as air. Again, we're oversimplifying things for a purpose. And then we go to the middle bubble, and that middle bubble is our liquid. And that liquid, look at this, the particles are kind of closer together, and the particles aren't really on top of each other yet, but they're pretty darn close. This is how I remember Wilmington, and this is how I remember Brunswick County. A few subdivisions, not many, a few houses that are next to each other, but they're not slammed on top of each other, with no way to even drive a vehicle. So the liquid particles are closer together. There's not as much empty space in between the particles. And then finally, over here to the right-hand side, that's the representation of a solid. And the solid particles are Wilmington today. I mean, they are stacking houses on top of houses. I'm surprised we don't have 40 floors of apartment buildings in town and around and about, because this is what a solid is. There's so many people, there's so many particles that are crammed together in a certain amount of space that there is no room to move. There's no room to breathe. Everybody hates each other, it seems like, in New Hanover and Pender and Brunswick County, but it's all due to the amount of space. And the reason that I bring it up is because if you pay attention to what I've been saying, limited space. Our empty space, not as much. Now we have no empty space at all, and they are corresponding the empty space to density. Because on this little teeter-totter down here at the bottom, yay, elementary school, I'm on the playground, the gases will have a lower density value than most of the solids. And the solids will often have the highest density value of the bunch. So if I'm going to relate density here to the states of matter, solids, for the most part, have higher densities than liquids, and those have higher density than gases. But here's the story. That's a lie! Look, I just complained about everybody lying to you. Now I did it too. But that's all right, because density, again, it's a take-home message. For the most part, is what I said. I did not say every single time. For the most part, solids have higher densities than mainly a lot of the liquids, and they have a higher density than mainly a lot of the gases. But that's not always necessarily the case. So what you're going to find here in this image is just a different visual for that same take-home message. As we go from gas to liquid to solid, our densities typically do increase. But the problem here is that they don't tell you the actual story. Because you can't compare apples to oranges. You're going to have to compare the states of matter with each other of the same material. And this makes sense. So what I've just done here is not really full out lie to you. I just didn't maybe clear it up. And the images don't clear it up. They never really say it either. But if I go back to this visual or I go back to this visual, what they're referring to are the densities and the state of matter of the same stuff. That is what this is all about. So now let's really compare apples to apples. Something that actually can correspond to each other. Let's say that I take a liquid, and in this case, water. I go into my kitchen, I put some water into a cup, and I calculate the density. All right, that's water. And then let's say that I turn it into a solid. All right. So if I go to a solid, I freeze it in the freezer. And this diagram is telling me that the solid, well, that density is going to go up. And then if I take this liquid and I put it into a spaghetti pot and I crank the heat onto it, and I begin to boil it, and I make water vapor, that's the gas, then it looks like my density will go down. Well, maybe. But if this was the case, oh my God, they lied to me again. Because if this was the case, if I took liquid water from the faucet, and if I freeze it, and it goes to a solid, then wouldn't that mean that in the cold, hard days of winter, that when these lakes and rivers freeze over, that solid water, which is what we would call ice, wouldn't that just sink down to the bottom and freeze all the fish and they would just float up on top? But why is the ice always on top and it's still water underneath? Oh, no. Okay, so here's the story. These are generally speaking. So what that means is that we want to keep in mind we compare apples to apples. We compare the same stuff. And then we can make a general statement. And that general statement is that gases normally, that's the key word, gases normally have a lower density than liquid of the same stuff. And liquids normally have the density values that are going to be less than the solid versions of the same stuff. All right. So now that we've kind of muddled the water, made it even more confusing, because now it seems like everything that I tell you, oh, there's an exception, oh, there's an exception, oh, generally speaking, again, it's a take-home message. That's what this is all about. But now that we understand this idea of empty space, now that we understand mass and the amount of volume that that material takes up, we can start to pick all of the pieces and combine them all together. So here's a test tube. And the test tube looks like oil and water and honey. Everything in my kitchen. And it looks like in this test tube, I've gotten 3 layers. The reason that this works, though, we, again, have to make a disclaimer. You've got to pick things that are immiscible, all right? If you don't pick things that are immiscible, then what's going to happen is that these layers are going to mix. They're not going to separate. And if they don't separate, you can't have which one sinks to the bottom. It's not going to work out for you. It's not going to work in your favor. They're going to mix together. It's going to make one layer. There is no top layer. There is no bottom layer. It's one layer. So immiscible basically means they do not mix. That's what that term means. So miscible means that they do mix. Hear the word mix in mixable. So 2 liquids, mixable, whatever you want to say. I don't care. So in this test tube, there are 3 immiscible liquids. They do not mix: oil, water, and honey. Oil has the lowest density value, so therefore it goes to the top. Water has like a middle density value, so it kind of hangs out in between. And then honey is much thicker. If you ever try to pour real honey out of a jar, you're going to sit there forever by the time it gets onto your toast or whatever you decide to put it on. But that honey is a little thicker. That honey is a little heavier. That honey weighs a little bit more in the amount of volume of space that it takes up. And because of that, that value of the density is higher than water and oil. And because of that, it settles to the bottom of the test tube. So density values of liquids, if they do not miscible, if they do not mix, we can rank them in order of low up on top to high down below. All right, so with that said, here's a nice little pretty image. I'd hate to be the person to clean up after this image is taken, by the way. And over on the left, we see the black letters, and the black letters all represent liquids. So it's saying, hey, we poured some lamp oil in here, and we poured some rubbing alcohol in here, and we poured some vegetable oil in here. We poured some water and some dish soap and some milk and some maple syrup and some corn syrup and some honey. And all of these layers begin to separate one from another. And the reason that the layers separate is because they're not miscible. They're immiscible. And because they're not miscible, they separate into layers. We can rank them in the order that they float. If you ever watched that It movie, Georgie floats. Okay. So this probably means that the lamp oil has the lowest density value of the bunch because it's floating on top. Georgie, Porgy. And then down here at the bottom, we see honey, and honey sinks because it has the highest density value of everything that they used in the diagram. Now, of course, there's things that have a higher density than honey that's out there, but this is what they chose. Pretty common ingredients. You know what the majority of them are. So we see nice, pretty layers. Now, keep in mind, they probably added food coloring because unless you're Homer Simpson living by the nuclear waste facility, you probably don't see water that's lime green. In addition to this, though, all of the red letters are going to relate to solid objects that they have dunked inside of this tube. These solid objects is a ping pong ball, and then we have a soda cap, and that's probably right there. Then we have some beads that are floating maybe right in there. Then we have a cherry tomato, that's that little red ball looking thing. Then we have a die. It looks like it's rolled on the side of three dots. Then we have a little popcorn kernel right here. And then a bolt down here at the very bottom. So what they're trying to tell you to do is, listen, if you knew the density values for these solids, you could compare the density values. And if you gave them an environment where they could kind of settle and float and go down to where they go down, they all will not crash at the bottom. They're going to stop around the same density layer that those liquids have. So what this means is that the bolt will have the highest density, so kerplunk, down it goes into the bottom of this nice little cylinder. Up on top, the ping pong ball has the lowest density value. I mean, after all, it's filled with air on the inside for most of them, so very lightweight. It takes up some space, but the mass is very low. So because of that, the density is very low. So out of everything, it floats on top, and it doesn't sink at any point in time. For this little popcorn kernel, okay, well, that takes up space. We can calculate the space. And it has mass, because we can calculate the mass. And then we can calculate the density, if we knew that. So I dunk the little popcorn kernel in, and it just... And then it gets to the maple syrup layer, and it's going to go, whoa, wait a minute. Here I find a density value that I like, and it's kind of same as my density value, so this is where I'm going to stop. So it floats, yes it does, but it's floating in the layer that's the closest to the density value that it has in its own right. So this is the take-home message of density. This is how we calculate density. But at no point in time have we talked about specific gravity. And I just told you that specific gravity is the most important. And here I've gabbed about density for 30 minutes because I'm leading up to that moment of specific gravity and what it all means. So in the next video, we're going to continue this discussion of density. And we're going to learn how to calculate density. We'll do some example problems, and then we'll finally get into specific gravity, which is really where it's all about.